All right, thanks. So shift gears again to talk about radiometry. I think we're going to have a few talks about radiometry here in sequence. So we'll start thinking about thermal emissions from the thing we're looking at. This is a talk about using microwave radiometry at frequencies from 500 megahertz to 2 gigahertz to try, one of our things we're interested in is trying to sense the temperatures inside of thick ice sheets, like in Antarctica or Greenland. And we're also interested in trying to sense sea ice thickness. And this project's been going for several years now. Many collaborators, including many up here at Liang Sang has been a big part of our team. Roger, who's going to talk after me, is looking at some other aspects of this technology with some other work. So let's start talking about this. So the science application that motivated this work, again, was sensing the temperatures inside of ice sheets, because that's a parameter that's not really easy to measure any other way. And it does matter because the temperature of the ice governs its stiffness, which then, if you're trying to model how ice sheets are going to evolve and deform over time, that's a parameter that's relevant to know. We also, along the way, realized that this technology is useful for sensing sea ice thickness as well, particularly in this range of up to about 2 meters, because that's an important, bigger fraction of the sea ice that's out there with the changing Arctic. So improving the ability to sense sea ice thickness in that region is another interesting application. So we developed this radiometer to do that. It's called the Ultra Wideband Software Defined Microwave Radiometer, or UWB-RAD is what we call it. And it was supported by a NASA Instrument Incubator program. Again, we measure between 500 megahertz and 2 gigahertz. We measure the thermal emissions in those bands. We've deployed this instrument a couple of times in Greenland. Fall 2016, fall 2017, we deployed it in Antarctica last year, about a year ago. And currently there's a version of it deployed on the Arctic sea ice flow as part of the MOSAIC campaign. That's an international sea ice observing campaign. And also a proposal for a space mission based on this idea was put forward in Europe under the Earth Explorer 10 campaign called the CryoRad mission. It wasn't selected in that round, but we'll see what happens in future rounds. And this is a project where we're building a new kind of instrument. We need to understand what kind of signatures it's going to measure. So it's been an extensive modeling effort that's been part of the project. And Professor Sang's been the leader of that. And his team here has done a lot of great work in trying to help understand these kind of signatures. So the idea is, thermal emission, when we have a microwave radiometer, the thing that's interesting about a radiometer is it can see through things that are transparent. And so the temperatures you're seeing come from a spread of the material inside of the object you can see through. And so our idea here was that an ice sheet, especially a very cold and dry ice sheet, is pretty transparent at low microwave frequencies. So by using multiple microwave frequencies together, the lower frequencies would see the temperatures coming from deeper in the ice sheet as well as those coming from shallower in the ice sheet, whereas the higher frequencies would only see the shallower portions. And so by measuring a wide band of frequencies, you could try and back out what the temperature profile is inside the ice sheet. The temperature is a function of depth. So, and typically what you'll see is the ice sheet is colder at the surface and warmer at the bottom. The ice is like an insulator. So at the lower frequencies, you should tend to see higher brightness temperatures. And at the higher frequencies, you should tend to see lower brightness temperatures because you're seeing more of the surface. And so that's the general physics that motivated us. Along the way, you also realize you could sense other parts of ice sheets and sea ice and so on. So we've also been thinking about those kind of applications. So again, we're operating 500 megahertz to 2 gigahertz, low frequencies from a lot of traditional radiometry point of view. Those are not protected bands except for the L band 1400 to 1427. There's a protected band there, but otherwise these are not protected bands. The heavily used part of the spectrum. So definitely interference is a big issue here. And the reason we think this is possible to do is because all the work that's gone on across many institutions, including about the development of technologies for removing interference for microwave radiometers. So to make it possible for radiometers, at least in part, to try and operate in these crowded spectral parts of the spectrum. So we built an instrument with that in mind. This is 1500 megahertz we're observing over. You could try and sample that whole bandwidth at once, but we instead chop the bandwidth into sub-channels. So we have a sample, we have basically a filter bank and sample all the channels in the filter bank simultaneously. Each channel is about 100 megahertz wide. To keep things easy, we just have one polarization looking at nadir for this instrument. and we made an antenna to try and, our idea was to keep the footprint of the instrument constant across frequency. So we have a wideband antenna with a uniform beam width versus frequency. And for this instrument, we do all the RFI processing in software. So the samples, we just take A to D samples, they go into the computer, and then we can real-time process those or post-process those into the final products. So we built this instrument. Here's a picture of it. The samplers are just a bunch of A to D boards and computers. So there's 4 computers here in that stack, plus an analog radiometer front end. So there's a picture of the rack. We have this, again, circular polarized antenna looking straight down. It just sticks out the bottom of the aircraft when it flies. And we've worked with Ken Bourque Airlines of Canada in our deployments. We've been on both Twin Otter and a DC-3 aircraft for the system so far. It's a relatively standard, well, not entirely standard, but the radiometer front end is this pseudo correlation type design. It's wide bandwidth. Okay, so traditional radiometer, we build narrow bandwidth. We want things to be, tune everything so it's well matched throughout the system, which makes it easier to calibrate a system and so on. When you go to these wide bandwidths, you kind of run into some challenges with that because it's hard to match things so well across a wide bandwidth. So we used this pseudo correlation type design that still has internal calibration sources and so on. And here's where we split into the filter bank over here. We have sub-channel filters for each of those to try and isolate out RFI between the channels. And then we go into the A to D, down convert each channel and go into the A to Ds in the computers. Here's a picture of the antenna. This is the radome of the antenna. Here's a picture of the radiometer electronics inside the box. That's the front end that was built, this front end up here. So this is the system we have. We've worked a lot on testing it out, calibrating it, and so on. Here's the frequency channels, 12 channels across this band, okay, between 500 and 2,000. We do have this gap in the middle here because on board the aircraft, there's a distance measuring equipment band there that's high power, so we decided to stay away from that. So we don't cover the entire band, but we cover a large fraction of that 500 to 2,000. Like I said, we just grab the A to D samples into the computer and process everything in software. The RFI processing that's done, for each of those channels has its own processing going on in parallel. It is because of that, we did decide that we could afford to operate not at 100% duty cycle. So the system's not continuously observing. It does grab data and process and then measure again. We operate about 10% duty cycle, but that's still on the time scale of seconds. And we're flying, we have a big footprint, flying low altitude, so we have plenty of time to look at a spot on the ground. The processor is basically forming spectrograms, like a lot of the RFI processors do these days. It can compute the kurtosis, kind of like the SMAP, if you're familiar with the SMAP RFI processing, does many similar things to that, has a full band kurtosis, has a sub-band kurtosis, has a pulse blanking, it has cross-frequency detection. So similar types of RFI processing algorithms where we're trying to look at what should be thermal noise and anything that doesn't look like thermal noise, flag it out so that we only have thermal noise left over, hopefully, when we put it through all this processing. And we can do that real time, but we also do it in post-processing. Doing it post-processing gives you more flexibility in retuning things and so on. But these algorithms do run in real time aboard the computers and produce a cleaned output as the system operates. Here's the flight path we used September 2017. So the instrument, Ken Bourque Airlines, is based in Calgary, Canada. So we start from Calgary over here, and we need to go to Greenland. So we fly up through Canada. We acquired data on all these flight lines and wound up over here in Greenland, Thule Air Force Base. We did flight. We wanted to observe sea ice in this campaign, so we went up here, and this was September, so we had to go pretty far north to get some coverage of sea ice. And then we had a flight back here over the ice sheet. We did cross some borehole sites where the temperature profile inside the ice sheet is known so that we could have some things to use for ground truth data, and made our way back to Canada on that flight path. So we did get, in addition to the ice sheet observations, we got sea ice, we got some land observations. We haven't done too much with the land observations so far. We're planning to in the future. We got a little bit of sea observations, but not enough to really draw many conclusions there. Here's an example of the RFI processing. Again, these are heavily used bands, not only from sources on the ground, but also on the aircraft. The aircraft has to do its communications and navigation systems. So this is a spectrogram here of about half an hour's worth. You can see here's the frequency, 500 megahertz to 2 gigahertz. We have our 12 channels here going across. And you can see this is calibrated brightness temperatures, okay? So the color scale is 120 to about 250 there. And you can see lots of funny looking stuff here that doesn't look like thermal noise. So you put that through your RFI processing algorithms and hope they can clean it up. And so after we put it through the processing, it definitely looks a lot nicer. So that's good. A lot of that interference was pulse type, which is relatively easy to get rid of. It's not perfect. There's still this spectrum isn't 100% flat, so we continue to refine things and tune the algorithms and so on. This is part of a scene where, if we look back at this flight path, when we came out of the Air Force Base, we would come out here over the ocean to get some ocean observations, and then come back onto the coast of the ice sheet, and then go back into the coastal part of the ice sheet before we continue on into the drier part. And so this portion is from that period. So down here we were over the ocean, come out over the sort of rocky part of the ice sheet, the coastal region. And then as you go into the ice sheet, at the edges, there's a lot of melt and refreeze that occurs. So even at these low frequencies, you get some scattering loss down here. But pretty quickly you come out of that as you move away from the sort of melt and refreeze zone and get into the drier part of the ice sheet. So show some results from that short. So here's if you go back, now notice when we went between these two, RFI processing is useful, but definitely we're losing pieces of the spectrum here, okay? So you do lose, when you don't have clean spectrum, you definitely lose, but you hope you can at least have something left over. So these are those 12 channels, okay? The 12 different frequencies. Blue is the lowest frequency and green is the highest. And we see, this is that same more or less period of time where we were out over the ocean here, come onto the rocky part of the ice sheet, and then here's this sort of scattering region. You get some spectral signature here across frequency, and then we come into the dry part of the ice sheet where things are much more stable, and we still see some spectral signatures there, and that spectral signature is what we're going to use to try and infer the temperature profile of the ice sheet. So throughout this project, we did learn from this that definitely our instrument's going to be sensitive to the temperature inside the ice sheet, but it also turns out it's sensitive to the details of the density fluctuations in the upper portion of the ice sheet. And so those are kind of nuisance parameters that impact our ability to retrieve temperatures. So as part of the retrieval process, we did, this is a plot of the retrieved temperatures inside the ice sheet. Okay, so we took that data set, we run it. The retrieval is basically a match up to a forward model, okay? And by doing that, you can retrieve the temperature inside. So this is depth inside the ice sheet going this way. So 1,500 meters thick where we start out on this part of the ice sheet and going to about 3 kilometers thick. So very thick ice sheet. And this is the temperature profile inside, going from about 250 or so to 270 kelvins. It gets warmer as you go closer to the bottom. To do this retrieval, we did have to, these are the borehole sites, okay? So we had 3 boreholes we flew over, and we can compare with the temperatures there. But we did have to use those truth temperatures to help us put some limits on the density parameters of the upper portion of the ice sheet. So this retrieval is not independent of the borehole because of these nuisance parameters that had to be inferred. But once we determined those parameters to match up with the boreholes, then in between, there's kind of tracking a smooth evolution algorithm that allows those density parameters to vary between here and here so that we can still retrieve the temperatures in between. And so this is a nice result we got. We're trying to get this investigated by some of our glaciology science colleagues to infer what it's telling us about the ice sheet. So that's one of our temperature profile results. As I mentioned, we're also looking at sea ice, trying to remotely sense sea ice thickness. In the world of sea ice thickness sensing, there's kind of one way of doing that is using laser LiDAR measurements, which ISAT-2 is doing right now. And the way that works is you measure the freeboard of the ice how high it's sticking up above the surrounding ocean, how high it sticks out, and thereby you can determine the thickness of the ice. That works well when the ice is thick enough. So there's this, if it gets too thin, that doesn't work so well. So the sort of laser altimetry method works for ice sort of in the 2 meters and above thickness, maybe a little thinner than that. At the same time, there's been emerging the L-band radiometry. SMOS and SMAP can measure thickness sort of in the 0 to about 50 centimeters range. But in between those two, neither one of them does that great in this sort of 50 to 200 centimeters range. And so we wanted to see how well we could do that. Here's our flight path in Greenland in that northern part. Again, we went out here over this flight path over sea ice. And unfortunately for this flight path, we didn't have ground truth. You know, sea ice is very dynamic. It moves around, changes all the time. There's not a lot of ground truth, so we didn't really have anything to compare against, but we did developed a forward model for the emission from the ice and did a retrieval. Here's the thickness we retrieved. Okay, so we can see here the thickness is sort of varying in the 0 to 2 meters range, okay, and varying in a way that seems plausible based on what we can tell from the radiometer measurements, as well as we have SAR data in the region that was acquired at a similar time. We can match those up and see what the SAR data tells us. This is a plot of all the brightness temperatures in this region. You can see a lot of fluctuation because it is pretty sensitive to the ice thickness. And we have some more sea ice measurements from Antarctica from last year where we do have ground truth, and we're currently working on interpreting those. And also we have our instrument deployed in the MOSAIC campaign where we'll get a lot more ground truth information just for a localized site, but it is we think we're moving toward a good demonstration of the sensing sea ice thickness in that range. In Antarctica, again, about a year ago, we have collaborators in Italy who were able to support a campaign through the Italian Antarctic program. We deployed out of Mario Zucchelli Station, the Italian base in Antarctica, and there we had a flight path over coastal regions around the base, as well as going into Dome C where there's a borehole and taking some airborne measurements around there. So we had a more extensive plan. The weather, of course, you have to follow what the weather allows you to do, but we still got a good data set here from Antarctica that we're looking at. Here's a zoom in on the flights around the Dome C borehole, which is going to be another temperature profile sort of a demonstration for us. And this is that coastal region. We got measurements over sea ice there, as well as some of these outlet glaciers and so on in the region. So we'll be looking at those. Here's a few example data sets. This was out over one of the portions of the sea ice flight. Again, the 12 UWB-RAD channels shown here, okay, in color. And we also have an IR measurement, so we can see generally they're anti-correlated to each other. The way things, sometimes they're correlated, sometimes anti-correlated, depending on what you're looking at. And we say comparable. At first look, they look kind of similar to the Arctic ones, indicating that we should get some retrieval information out of this. We have a paper that's been, it's online now about the sea ice retrievals from the Arctic measurement, from the Greenland measurement. We took a quick look at the data over this outlet glacier. Okay, so this is flying down this Priestley Glacier in Antarctica. Here again are the 12 UWB-RAD channels. We again see some spectral signatures here that vary depending on what you're looking at, and some general, higher and lower trends that were interesting. We matched, it turns out Operation Icebridge had flown its radar over this same glacier, not at the same time, at a different time, but we could compare the Operation Icebridge radar grams, okay, so these are versus depth, versus what we measured. And indeed, we tend to see that when there was dark here, it actually indicates more scattering. So when there was more scattering, we got lower brightness temperatures as one would expect. So that was nice to see this correlation to show us that these results were at first look reasonable. And as I mentioned, we have this, a copy of this instrument, which actually, instead of having 12 channels, just has 4. So it's 4 channels spanning that region that, occupy, they're still 100 megahertz wide, but taking samples of the 500 to 2000 megahertz region. It's on a tower and was deployed through this campaign aboard the German vessel Polarstern. So currently on Arctic sea ice, although actually and the campaign has multiple remote sensing instruments. There are multiple scatterometers, multiple radiometers, a wide set of instruments deployed from an international group of investigators. Actually, a big lead just opened near this camp. And so the camp currently is shut down while they relocate all the instruments away from this ice flow that may be floating away. So we're waiting to get things reestablished, but so far it seems like things were going well, and we'll see some data from that measurement. As I mentioned, our Italian collaborators have formulated a space mission to deploy a wideband radiometer called CryoRad. The PI was Giovanni Massaloni of CNR in Florence, with the same sorts of science applications. Now, there are other applications you can envision for this type of system, but the primary ones were the cryospheric ones. It's definitely a challenging measurement to make for space because of the low frequencies. It's radiometry. If you want to have decent resolution, you need big antenna at these low frequencies, right? So the antenna is definitely something that needs to be thought carefully about. But there was a proposal to have a 10 meters, order of 10 meter deployable reflector antenna. And definitely the RFI is also a significant question, but we're talking about a mission focused on cryospheric measurements, where it's reasonable to assume that the interference should be less than it would be over many other parts of the globe. So this mission got good reviews, wasn't selected, but we'll continue to refine that and see what we can propose for the next round of this. So, and here's the orbit. It was an orbit focused on coverage of the cryosphere. Okay, so this is, we feel this is an interesting technology. The things that have enabled it are a lot of the interference, ability to deal with interference that has been developed over the past decade or so is relevant for this. It makes it possible. And we do think there's something to be learned from measuring these bands, because of their lower frequencies enable you to penetrate things more than other bands. In particular, we think the ice sheet temperature and sea ice thickness sensing are good applications. There's a growing interest in these measuring these sorts of bands that's occurring internationally, and so it's nice to see that. And there's also an interest in sensing sea salinity, because the lower frequency you go, the more sensitivity you get to salinity, even in cold waters. So I think things are developing in this area, and we'll see more activity in the future. And so here's a few papers you can take a look at, and I'm happy to answer any questions. Thank you.
Okay, questions?
Yes.
Yeah, so with like atmospheric profilers of temperature and humidity and things like that, there's this formal mathematical way to calculate vertical resolution from the behavior of the functions and everything. Have you done something like that with your temperature profile to see what kind of vertical resolution you're getting?
We had set a science requirement on ourselves to retrieve the temperature profile at 100-meter reporting intervals.
Yeah, that's not the same.
Now, the retrieval that we do,
Interpolate, make it 1 inch.
the retrieval we do is a parameterized retrieval. So we are retrieving parameters of the profile. So the translation is done in terms of how much sensitivity do you get in those parameters, how much accuracy do you get in inferring those parameters, and then how does each parameter map on to how the temperature profile varies at each depth. And I would say I don't have an immediate answer to say for that at the moment, but
I mean, are there 2 or 3 independent levels in that thing, or a half dozen, or?
It's the number of parameters that are used in the model is there's 5 parameters. So, and the model that's used is an ice sheet physics-based temperature model, which based on the surface temperature and the heat flux at the bottom. So, yeah, it's whatever you want to interpret about the temperature profile retrieval. It flows by first retrieving those parameters and then how that maps onto the properties of the profile.
Any other questions? All right.
Okay, thank you.